In this short lecture, we explore the mathematical idea of the conjugate. The simple factoring a squared minus b squared is a plus b times a minus b has lots of applications. This is the so-called difference of squares formula. The fact that a difference of squares factors into a sum times difference. Note that we're using three different operations: addition, subtraction, and then we're multiplying these together. This means that we can often manipulate square roots, for example, using this formula. For given an expression a plus or minus b, we often speak of the other piece, a minus or plus b, as the conjugate. So the conjugate of a plus b might be a minus b, while the conjugate of a minus b is a plus b. For example, the cosine of 75 degrees is, using a sum of angles formula, exactly equal to 1 over the square root of 6 plus the square root of 2. If we don't like square roots in the denominator, we can multiply both numerator and denominator by the conjugate of that denominator by square root of 6 minus 2, and the denominator becomes square root of 6 squared minus square root of 2 squared, or 4. Our difference of squares turns out to simplify. So another form for the cosine of 75 degrees is this form we originally had: multiply by the conjugate and simplify. So the square root of 6 minus the square root of 2 over 4. Those are equivalent to the original fraction. The conjugate is sometimes a useful way in trying to compute limits. For example, suppose we have this limit as x goes to 4. If I attempt to plug in x equals 4, the denominator becomes 0, and so my expression is undefined. But if we take that denominator, square root of x minus 2, and we recognize that it has a conjugate, square root of x plus 2, and so multiply both numerator and denominator by square root of x plus 2, then the original expression becomes this expression. Notice that when we multiply by the conjugate, the denominator simplified, and now as long as we are not at x equals 4, we can cancel or divide out the x minus 4, and so we have this expression, and we're ready to plug in. Plug in x equals 4, you get the square root of 4 plus 2, which is 2 plus 2. My final answer is 4. We evaluated this limit by multiplying numerator and denominator by the conjugate of the denominator and then simplifying. As I said earlier, given an expression a plus or minus b, the other piece, a minus or plus b, can be thought of as the conjugate. So when we simplified this expression on the last side, we multiply by the conjugate of the denominator. Conjugates are especially useful in working with complex numbers. If a and b are real numbers, then the conjugate of a plus bi is a minus bi. And if we're working with a complex fraction where we have a denominator and we want to put everything into Cartesian form or rectangular form, x plus y times I, we can do that by multiplying numerator and denominator by the conjugate of the denominator. For example, if we want to simplify 3 plus 4i divided by 1 minus I, we look at the denominator, we look at the denominator downstairs, 1 minus I, and take its conjugate. Its conjugate is 1 plus I. So we're going to multiply this fraction by 1, written in this form, 1 plus I over 1 plus I. We're going to multiply numerator and denominator by 1 plus I. This does not change our expression, but it allows us to simplify it. So our work will look like this: 3 plus 4i divided by 1 minus I, multiplied by the numerator and denominator by the conjugate. The numerator will be 3 plus 4i times 1 plus I. The denominator will be 1 minus I times 1 plus I. Because of this difference of squares formula, the denominator now simplifies to 2. Meanwhile, I work out the numerator with a little bit of algebra. It's minus 1 plus 7i, and there's my answer. The idea of the conjugate appears in a certain limit we need in calculus. The limit of 1 minus cosine x over x as x goes to 0. Note again, with this limit, if you plug in x equals 0, it's undefined. But we want the limit as x goes to 0, so we need to manipulate this in some way. Well, we can multiply numerators and denominators of this fraction by the conjugate of the numerator, 1 plus cosine x. If we do that, then my expression becomes 1 minus cosine x over x times 1 plus cosine x over 1 plus cosine x. The numerator can be cleaned up a little bit, difference of squares, 1 minus cosine squared, and so on. But by a Pythagorean identity, 1 minus cosine squared x is the same as sine squared x. So I can rewrite the expression this way, and then I can break it up into two fractions. I can think of it as sine x over x times sine x over 1 plus cosine x, and then I know the limits of the pieces. We know that the limit as x goes to 0 of sine x over x is 1, and the other piece I can just plug in. The limit of as x goes to 0 of sine x over 1 plus cosine of x is 0. So I've written this original fraction that I started with into a product of these two pieces, and I know the two pieces, their limits. Their limits are 1 times 0. So the limit of this expression after this little bit of work gave me that, and now it's going to be 1 times 0 or 0. So I found a way algebraically using the conjugate to simplify this original fraction. This identity, the difference of squares, shows up in many, many areas of mathematics. Be alert for opportunities to use it.